showing my diagram. That's cool. All right, so for the video's purpose here, we'll review again. Catalyst speeds up a reaction. What does it do? Decreases activation energy. What does that mean? All right, well, if you start here at AB and you got to get to the top, what's that called? The top? Activated complex. If you need to get there to start those effective collisions, the catalyst actually shrinks that. It lowers the peak. But these spots don't change. Your reactants and products do not change. Okay, you still have the same reactants, still get the same products. They still emit, release, or absorb the same amount of energy. So the delta H, in this case negative 30, doesn't change. So when we're drawing a catalyst, and again, if you don't have this, I need you to get this in your notes. You start at your reactants, that doesn't change. You draw a dotted line underneath, you kind of mirror the curve, right? You do the same curve the best you can, and then you end at your products. So this dotted line, the biggest mistake kids make on Regents is they bring the dotted line under the entire curve. So what kids like to do, which is wrong, I'm going to be clear here, I'll show you what to do, or what not to do, I should say. A lot of kids will do this on Regents. They'll do that, and they can't get credit because that's showing the reactants and products changing their energy. That's not true. That doesn't work. It doesn't work that way, sorry. You have to start at the reactants and end at the products. It's the line in between them that shrinks or gets a little bit lower, okay? Am I being clear with that? I hope? Yes, some of you say yes, okay. So I just want to be clear because it's pretty common that's on a Regents. They'll give you a diagram and they'll say, show how a catalyst changes the diagram. And you have to draw with a dotted line. So I don't want you getting that wrong because it's not that hard, I don't think. You just have to remember it starts and ends at the same spot. And again, my whole thing all year, don't memorize, understand. What is understanding? The energy doesn't change. The energy doesn't change, it just reacts faster. All right? So that's how we would draw that. Last couple of things I want to add to our notes on the catalyst. Some of it I've already said. A catalyst does not react, meaning it isn't consumed. It does not react, is not consumed. It doesn't take part in the reaction. I used the analogy of a teacher or a coach yesterday. All right, I can't play in the basketball games. I can't take the Regents exam. Right? I can help my players get better so they can play better. I can help you learn and become better students so you can perform better on the test, but I can't actually take part in the test or the game, right? So that's the analogy there. So I can facilitate, speed up the learning and playing and process or whatever you want to call it, but I can't actually take part, right? So catalysts do not react, it's not consumed, so catalysts can be reused. They can be reused over and over again. Do not change the delta H. That's what I just spent some time on. The energy released or absorbed, it's still going to have the same amount of energy. It's just going to release it or absorb it faster. That's all. All right, you know, not a great analogy, but just think if you're driving slow or fast, right? So I drive from home to here every day. Whether I drive slow or fast, the time might change, how long it takes to get me here, but my house doesn't change and the school doesn't change. That's what I mean. Reactants products don't change. So that's why that doesn't change. The amount of energy doesn't, the mileage doesn't change, right? The time might, but the mileage doesn't. That's a better way to kind of explain that. That's going to be the same. You can just do it faster or slower. All right? All right, make sure I'm not forgetting something because sometimes I don't look at my notes and I just go off my top of my head here. Oh, one more thing I want to put. Catalysts do not start reactions. They don't start it, they just speed it up. You need activation energy to start it, right? So catalysts don't do a whole lot except speed up the reaction. That's it. They speed up the reaction, and that's the key right there. Okay? Decreases. It brings that peak down, so it decreases the activation energy. Provides that alternate path, that other pathway, a shortcut to get to the products. All right. So when I added the catalyst to the graduate cylinder yesterday, right? That was yesterday. Yeah. So it foamed up pretty good, and that's because it started reacting much more violently and much faster, right? So it was very clear in the demo as soon as you add the catalyst, it starts to react, right? So that was the point of that. Questions on catalysts? What's the opposite of a catalyst? Inhibitor. Good, right. That was on the homework. All right, we are done with kinetics. All right. Good stuff. Now tomorrow, I'm going over the bonding test. So make sure you bring that tomorrow, okay? Got about 15 minutes. We're going to start new topic. Equilibrium. All right, equilibrium. Okay, what is equilibrium? Equilibrium is a chemical or physical process that is reversible. That's the best way to explain it in one sentence. A physical or chemical process that is reversible. And I'm going to show you something today to kind of give you a visual of this happening. Okay? Chemical or physical process that is reversible. So as far as physical is concerned, so for physical examples, all phase changes. All phase changes are in equilibrium, as long as the temperature isn't changing. So what do I mean? I'll give you a couple examples. So at 0 degrees Celsius, you have H2O solid turning into H2O liquid, right? So at 0, ice melts. But if it's stuck at 0, right? If you have a condition where the temperature is at 0 and it's not changing, what actually happens is the reverse. Liquid, so water, freezes into ice, and it constantly goes back and forth. And I use the analogy of a revolving door. I've used that before with you guys with vapor, evaporation, and condensing, the dynamic equilibrium. That double arrow means reversible. That's your forward, that's your reverse. And if you keep temperature at 0, that happens continuously, simultaneously, right at the exact same time. Okay? So that's one example. All right? Another example, so that's just freezing. You can do boiling, subliming, any of the phase changes. I'm not going to write them all down. But another example would be saturated solutions. Saturated solutions, and if we have an example of salt. So if we have NaCl solid, and we dissolve it in water, so we have an arrow going this way, we would have NaClAQ. So if we take salt, we put it in water, we can actually write H2O on top of the arrow. That means we're putting it in water. So if you have salt, you put it in water, it becomes NaClAQ. Well, if it's saturated, what actually happens at a molecular level, you can't see it with your eyes, is it's crystallizing at the same speed, at the same rate. So your salt is dissolving, just like the ice is freezing, the ice is melting, and now your salt is crystallizing at the same time, and it's going back and forth constantly. Again, the two arrows represents reversible. So this word equilibrium means this, okay? We're going one way, we're going the other way, literally at the same time. So if you have a revolving door, like in a hotel or whatever, and you have a line of people inside and outside, every time someone walks in, someone walks out, and the door is constantly revolving, and the people are constantly moving, that's how I want you to think of this equilibrium stuff. All right? So we're going in, we're going out, we're going in, we're going out. These are just two examples of physical, right? We're not changing chemical compositions. All right? So, questions so far? Starting slow, trying to keep it simple. All right, so again, I want you to think revolving door, people going in, people coming out at the exact same time. That's called simultaneous, right? So this is simultaneous. All right. Now, chemical works the exact same way, except it's chemical. In other words, it's chemical reaction. So chemical, this is what we focus on mostly. Chemical equilibrium. I could use a whole bunch of examples here. I don't know. I'll just use the formation of water, let's say, or we'll do ammonia. Let's go N2 gas plus H2 gas forms NH3. We just have to balance. What do we need? We need 2 here and a 3 there. So again, your forward reaction is the formation, that's synthesis of ammonia. The reverse reaction is decomposition. So if you see something like this written on the board or on a test or quiz, homework, lab, whatever, this is chemical equilibrium. The first two examples were physical because it's melting, freezing, and dissolving. You're not, that stuff is physical. You've learned that already. Since the beginning of the year we talked about it. This is chemical because you have reactants, products, changing composition, right? Something new is being produced, okay? But the key here is we have to make sure we can really explain it the correct way. I don't want you guys just saying the forward and reverse are happening at the same time. That's great. Again, the revolving door. Imagine this is your revolving door. But the way I want you to word it is like this. So write this down word for word. The forward reaction rate, right? So the rate of the forward reaction rate is equal to the reverse reaction rate. So the forward reaction rate is equal to the reverse reaction rate. So the key here that I'm trying to get you to understand, which we've already learned about, this is why I teach this right after kinetics, is this word rate and equal. So rate means how fast it's going that way, right? So these are combining to make ammonia at the exact same time and speed that the ammonia is breaking down into those two. So it's literally going back and forth at the exact same time. What does that mean? It means the rates are equal. That's, again, the visual, the analogy of the rotating door, revolving door. Is if one person's going in, one person's coming out at the exact same speed and time, that's equilibrium. And now here's my question for who's not paying attention. All right, Jake, you ready? You got it.
Yes.
You're a smart kid. Let me pay attention. Okay, the analogy of the revolving door. You can visualize that?
Yeah.
All right. So if you have some people outside, some people inside, right? And if the people going in match the people going out. So they're going in, they're going out literally the exact same time. So these 4 particles are going in, these 2 particles are coming out at the exact same time. Everybody with me? Getting excited. It's important. What changes? Does anything change? Does the amount of this and the amount of this change, or does it stay constant?
It's constant.
Why, Jake?
Because I don't know, stays the same, I guess. I don't know how to answer that.
If you have, again, let's use the analogy of people. Let's say we have 3 in 1, that's 4 people here, and we have 2 here. So eyes up here, okay, this is important. This is the whole concept. Besides this phrase, the next thing we're going to write, these 2 phrases, explain the whole topic here. So if you have 4 people walking that way, and 2 people walking this way. So now you have 4 and 2, just like you had 4 and 2. Does anything change? Let me say it another way. These two produce 3 and 1. So every time these reactants make products, these products make reactants. So another way, again, another way to say it is, when the people are constantly changing, does anything change? The point I'm trying to really hammer home is no. Why? The explanation is why.
Because the amount going in is equal to the
Sort of, but not really. Is 4 equal to 2?
No.
No. So the amounts are not equal, they're constant is the word. The word is constant. The word is constant. So what I'm trying to get you to understand is if you have these reactants forming these products, and these products forming these reactants constantly, nothing ever changes. Because you're going to have 4 making 2, 2 making 4, 4 making 2, 2 making 4, and it never changes. It's like an endless line of people going in and out, and there's never a change in the amount on either side. Now, This side, 4, has more people than this side, 2. But if you're constantly switching, nothing ever changes. So what we're writing is that the concentration, write this down please, concentration of reactants and products stay constant. Stay constant. Encircle that word constant. The concentrations cannot be equal. 4 does not equal 2. I don't care what weird math you learn now. 4 does not equal 2. But 4 and 2 can stay constant. I use the analogy of a seesaw. And I have like a little balance. I have a little mini seesaw I put up here. I'll put it up here tomorrow. I have weights. I start moving them around and help teach this concept. So if 4 people on this side of the seesaw balance 2 people on this side, that's what we say is constant. So if we're constantly switching at the exact same time, the seesaw will never be out of balance. It'll always be constant because 4 is balanced with 2. Now in the analogy, it's based on weight, right? Seesaw, so you can say, okay, these 2 are heavier than these 4. That's irrelevant, but the concept is we want to keep that seesaw balanced, and that's what equilibrium means. Is every time you form products, your products are forming reactants. So the 4-to-2 ratio, so remember the ratios we learned. Stay with me. I know I'm saying the same thing over and over and over. This is really important. Okay? If you can memorize these, I'll just say it, you'll get like almost all Regis questions right on this. Okay? These are the 2 biggest concepts. There's something else we have to learn tomorrow, probably Monday, that we apply to this. But this is really important. So I'm going to just say it one more time. The mole ratio 4-to-2 never changes. If you're always making 2 and always making 4 at the exact same time, it's always 4-to-2. So that word means constant, right? Or that means constant. Not equal. Not equal. What's equal is how fast they do it. So the speed is equal, but the amount is constant. The amount is not necessarily equal. I'm trying to make that very clear. These numbers are not equal to each other. Okay? So that's the big difference between these 2. All right, I'm going to stress that the next few days. All right, let me show you a reaction in the back that kind of explains this. Let's write it down first, then we'll go back. And then that's going to be it, I guess. So, here's the reaction I have in the back. HCl plus NaOH yields H2O plus NaCl. That's the reaction I have in the back. Really, the overall reaction of this is actually this. H plus OH minus yields H2O, which is HOH. Go ahead and write both of those down. And I'm going to show you with the acid. That's acid plus base yields water and a salt. This is a reaction you will know no problem down the road. But acids and bases always make water. You mix acids and bases, it produces H2O. But they're reversible. Come on back, let me show you. You guys don't really need glasses. Just stand kind of